So before we get into set operations involving three sets, an easier way to think of union and intersection. Union is addition in regular math. In set theory, we call it union. In algebra, it's just adding things. In set theory, upside down U is intersection. In regular algebra, that would be multiplication. The specific term would be cross product. Now, we won't get into the details of it, but the reason why I'm mentioning this is for you to understand set operations and the order of operations. Let's take 5 plus 7 plus 3. Is it fair for me to say that this would equal to 5 plus 7 plus 3? Absolutely. No matter which way you put it, 5 plus 7, add it first, then you add 3 to it. It's the same as saying you have 5, add 7 and 3, and add it to 5. So it doesn't matter, 15 will equal 15. So absolutely. Let's extend this idea to a letter. Move away from numbers and use variables. I can extend this as A plus B plus C is equal to A plus B plus C. They are the same, so great. So when I first started, I mentioned that U is addition, inverted U is multiplication. So I'm going to simply change all lowercase letters to uppercase letters because in set theory, we use uppercase letters. It's common practice. Now I'm going to change the addition to union. So I have A union B union C, A union B union C. Are those two equal? They are. So you can see how I moved from regular numbers to variables and transition from algebra to set theory. So in a similar manner, if I have five plus 7 times 3, that would equal to 3 times 5 plus 7. Would that be equal to 3 times 5 plus 3 times 7? Now, the dot decimal is not decimal, it's times. So is that statement true? Yes. 5 plus 7 is 12. and I have 12 times 3, followed by 3, 5 plus 7 is 12, 3 times 12, 3 times 5, 15, 3 times 7, 21. So they're all the same, 36, 36, 36. Going from here to there, we have a name. What we just did is we distributed the 3 through, and we wrote it as 3 times 5 and added it to 3 times 7. Going to take that bit and replace the numbers with constants or variables like I did earlier. So let us observe closely, compare the one with the letters and the numbers, and ask ourselves, well, is the last statement true? Yes or no? Absolutely. They are one and the same. We can simply compare to the previous case with the numbers. We can extend this idea that we did with variables to sets. Now, my goal is to write an expression like the one containing A, B, C, but instead of addition and subtraction, we want to go for sets. We're going to use uppercase letters, unions, and intersections. In terms of set notation, I'll just change, lowercase to uppercase, addition to multiplication, addition to union, multiplication to intersection, and that's it. We have 3 sets, and we want to find A complement, B complement, C complement. Of course, anytime we want to find complements, we must have the universal set. So A complement will contain elements that are not in A, but are in U. So A, B, C are in the set A. 1, 2, 3 are in the set A. So whatever that's left behind will be a complement. -3, -2, -1, 0, 1/2, 1/4, 1/8, 4, 5. Similar manner, want to find B complement, we have to exclude all elements that are in B. So -1, 1, 0, 2, whatever that we leave behind will be in B complement. And lastly, C complement, we want to exclude all elements that are in C from the universal set, and whatever that remains would be C complement. There are only 3 elements in C: 1/2, 1/4, and 1/8. Therefore, we have -3, -2, -1, 0, 1, 2, 3, 4, 5, A, B, C. It is often a common misconception that if you have 3 sets and the universal set, if you combine all of them, you will always get the universal set. Not true. This goes back to the lecture on Venn diagrams, where A, B, C could be stars, galaxies, planets, and whatnot. Just because you put them together, it doesn't make up for the entire universe. They're still parts of you. Now, could they be you in some cases? Yes, it could equal the universal set in certain cases, but I did not design this problem that way. So we want to find A union B, union C. So we've got to do it piece by piece. It doesn't matter whether you have A union B first, then combine with C, or you switch the order and do it this way. We did this earlier. So first, I'm going to find A union B. So I've got A, I've got B. I just have to combine the two. So I have -1, 0. I've got 1 and 2 in both A as well as B. So 1, 2, 3, and A, B, C. So since I have a 1 in both A and B, a 2 in both A and B, I simply put 1, 2, and the remaining elements. Now I want to combine that set with C. So A union B union C would simply mean I'm going to take that set and merge it with the set C. The set C has the elements 1/2, 1/4, and 1/8. So I have -1, 0, 1, 2, 3, A, B, C, 1/2, 1/4, 1/8. That would be the A union B part. That would be the set C, and I'm merging them together. So we've got to note here that whether we do A intersect B intersect C, or A intersect B intersect C, they are one and the same, because intersect intersection is like multiplication. So A intersect B is the same as A times B. So A times B is the same as B times A. So we did this earlier. So I'm going to just keep maintaining the order and go with what I have. So A intersect B would give me the elements that are in common between A and B. So A intersect B is going to pick the elements that are in common between A and B. So we've got 1, we have 2. So we'll need this, so we'll just carry it around from here on out. Okay, there we go. Group. Okay, so A intersects B, we simply have to pick the elements that are common to both A and B. So have 1, 1, 2, 2. So A intersects B is simply 1 and 2. The set C has 1/2, 1/4, and 1/8. And we want to find A intersects B, intersects C. What is common between 1, 2, 1, 2, and 1/2, 1/4, and 1/8? By all means, nothing. So it is the empty set. So we want to find A complement union B and complement. Now, a couple of ways to do this. One way is to distribute the complement. So one can do A complement complement. When we apply the complement to the union, it becomes intersection, followed by B complement. If you take the complement of a complement, those two would go away. You'd simply have A. So think of it this way. We have a bar and we have A and A complement. The complement of A is right here, but if I took the complement of the shaded part, I'll go back to where I started, A. So the complements would sort of cancel out and you'd have A intersect B complement. We have A and we have B complement from earlier. So that's B complement, and A is simply A, B, C, 1, 2, 3. And now we want to find the intersection. So what is common between A and B complement? We've got A, we've got B, we've got C, we've got 3, and that's about it. So A complement union B complement would be equal to 3 A, B, C. That is one way of doing it. There is another way, which is the direct approach. I'll put it as method 2. Or I'll call it alternative approach. The other way of doing this problem is to first find A complement union B. So we first look at A complement. Then we look at B. Now the step is to combine. So we are going to find the union of the two. So A complement union B would contain all the elements of A and all the elements of B. So -3, -2, -1, 0, 2, 1/2, 1/4, 1/8, 4, and 5. We want to find the complement of the set that we just found. And I have the universal set here. Oh, yeah. So put it right there. So if I want to find the complement of A complement union B complement, so I want to pick elements from U that are not in that are not in A complement union B. So three is in A complement union B, -2 is, -1 is, 0 is, 2 is, 4 is, 5 is. So once I forgot, 1/2 is, 1/4 is, 1/8 is. Once I take care of those, I will end up getting three A, B, C, and 1. This sort of tells you that we've sort of made a mistake somewhere. So in the first part, I've got to add 1 here. So we must have 0, 1, and 2. So we'll have to get rid of 1 also. So we will have 3 ABC. So as you can see, doing it using both approaches sort of is useful in case you make a mistake. But some might prefer this approach. Others might prefer that approach. So finding a complement, finding or using B, finding a complement union B, and then finding the complement of a complement union B right here. But regardless of the approach, you will get the same answer. You have to get the same answer. I'm simply going to take the effective approach. Instead of doing multiple parts, I'm going to distribute that complement, and I'll simply have a complement. If you apply the complement to the intersection, it becomes union. B complement, and we'll simply end up having A union B. So by all means, all we're doing is finding A union B. Could we do it the other way? Absolutely, but I personally prefer this approach. So we have A, which is ABC 1, 2, 3, and B is negative 1, 1, 0, 2. If we put them together, we will have negative 1, 0, 1, 2, 3, ABC. Now, if we try to do it the other way, you will have a lot of extra steps. So you have to pick and choose. Is this way always the better approach? Not necessarily. In some problems, the approach that we did is better. In others, perhaps the alternative approach is better. So one may ask, well, how do we know? Well, it comes with practice. The more you practice, the better you would understand and pick out which method will work for you the best. This is one of those problems where one may say, well, I'll go ahead and do A intersects B complement. I'll distribute and write as A complement, flip intersection to union and followed by B complement. Sure, you can take that approach, but in my opinion, this problem is easier if you just go at it the way it is. First, find A intersects B. Well, A intersects B will simply be 1 and 2. So you pick everything from the universal set except 1 and 2. Oh, no. Oh. Go for this. So from the universal set, I am going to select elements, all elements except 1, 2. So that would mean get rid of 1, 2. The remaining is what we have. So let's erase. Move that over. So that would be A intersect B complement. And we want to find C complement. Well, C complement is all of you accept those three elements in C, 1/2, 1/4, and 1/8. So that would mean, I believe we did find C complement already. Yes, so that would mean C complement is right here. And we just have to find the union of the two. So combine. So if I put them all together, you just merge all the elements. So I would end up getting -3, -2, -1, 0, 1/2, 1/4, 1/8, 1, 2, 3, 4, 5, A, B, C. And that is simply a universal effect. So if we do A intersect B complement, union C complement, we would end up getting the entire universal set. So this is yet another case where you can pick and choose as to which approach you want to go with. I'm going to look at A union B and take its complement. I personally feel that that would be easier. So A union B will be -1, 0, 1, 2, 3, ABC. I want to get rid of those elements from U and put the rest. So I'll have -3, -2, 1/2, 1/4, 1/8, 4, and 5. So those are the elements that are in U, but are not in A union B. In a similar manner, I could do A union C. So A is ABC 1, 2, 3, and C is 1/2, 1/4, and 1/8. So A, B, C, 1, 2, 3, 1/2, 1/4, 1/8. And I would like to find the complement of that. So I want to exclude all of those elements that I see in A union C from U and leave the remaining elements. So I'll have -3, -2, getting rid of A, B, C, 1, 2, 3, 1/2, 1/4, and 1/8. So -3, -2, -1, 0, 4, and 5. And at this point, I would like to find the intersection of that term and that term, or that set and the other set. So we just have to find the terms that are in common. Have -3, have -2, I have 4, then 5. So the result is -3, -2, 4, and 5.